All right, we're gonna get into another example of a rational polynomial inequality. And I wanna do this one in particular because we haven't done any infinity tables with a factor that has a negative coefficient. And when a factor has a negative coefficient, we're gonna see that something different happens. There's a rule that we have to apply to make sure we get the correct answer. So in theory, it's pretty much the same thing like with linear inequalities. When we have a negative coefficient, something different happens. Now here, you can see the negative coefficient is -8. -8 is multiplying the variable, so that makes -8 the negative coefficient. And the inequality is gonna be a less than 0, meaning it's gonna be, we're looking for the negative solution set that satisfies the inequality. All right, so we know that with a negative coefficient, something flips, something switches, and we're gonna get to that. But for now, the first thing we wanna do when we have a rational polynomial is transform the function, this form of the function, into a factored form so that we can do the infinity table, right? All right, I'm looking at the denominator and I'm seeing that it's a cube, right? So the first thing I want to do is expand the function so we can see everything multiplying each other since we care about the factors. And then of course we're going to keep that numerator the same. It's only one thing, -8x. So now we got -8x over x plus 1 times x plus 1 times x plus 1. All right, bet. Now we want to make sure we get the individual factors so that when we go to the infinity table, we have every row that we need to account for. So the first factor is going to be that numerator, -8x. And then there's three more factors, which is 1 over x plus 1 cubed. So 1 over x plus 1 times 1 over x plus 1 times 1 over x plus 1. Now we converted that original rational polynomial function into its factored form. Cool, now we're making progress. What do we do after we get the factor form? Now we're gonna get the zeros of the function. And remember, when we're dealing with that rational polynomial, we get our normal zero, which is gonna be in the numerator, but then we have to get the zeros in the denominator. Remember, the actual factor is not gonna be a zero, right? Because 1 over x plus 1 can never be 0. Instead, we're looking for that denominator to be 0. And those are gonna be the zeros. So now we solve for our zeros, -8x. We divide it on both sides so that x is equal to 0. And then we solve for x plus 1, subtract 1 on both sides so that we get x is equal to -1. And those are gonna be the zeros of the function. All right, bet. Now we know the next step. We got our zeros for the function, which means now we can construct our infinity table. All right, now we got to count the rows. There are 4 factors and then the product combination. So altogether, there's going to be 5 rows. And of course, we're gonna get to the aesthetic part. You know, my favorite part, I gotta activate that infinity table. So I'm gonna write the real number line in the top left corner, and then I'm gonna write my arrows in. All right, you know the next step. Now we gotta put our zeros on the real number line from least to greatest. Now it should be -1 and then 0, but obviously I'm making a mistake right here. But the good part is that I typically recognize my mistakes eventually because something is not going to be right in the infinity table. Now here's the thing, if you notice from all the other infinity tables, when I start writing my factors in the rows, I put the ones on top, the factors that are going to be on the top is the one that corresponds to the lower value 0 of the function. So you can see I put 1 over x plus 1 in the top rows because that corresponds to -1 being the lower function. So this means I'm gonna eventually catch my mistake. And it's very important for when you solve these mathematical problems, especially these long-winded mathematical problems that you have self-correcting methods. This just happens to be one of them for me. So I'm gonna notice when I'm about to put my dot for the 0, wait, no, this is not adding up because it should be -1 first. So here I erase it. Now I'm gonna have -1 as the lower value 0, and then 0 as the greater one. So here, all right, now we're ready. I corrected my mistake. Now I'm gonna put my dot under -1 for the factor 1 over x plus 1. Cool. And then the rest of the factors are the same, so it's gonna be the same dot under the -1. And then for -8x, we're gonna put that open dot under the 0. Cool. Now, negatives on the left side, positives on the right side of the dot. But here's the twist. Now we got a negative coefficient, so we're gonna flip it. Positives are gonna be on the left side, and then negative is gonna be on the right side of the dot. And that's the only difference for when you have a negative coefficient factor in the infinity table. So let's do our multiplication. Negative times negative is positive, positive times negative is negative, and negative times positive is negative, right? Then for the next one, it's all positive. And then for the last one, it's positive times positive times positive times negative. So that makes it negative. What do we want? We want negative. So we check the negative boxes and X for the positive one. Cool. Now we can write our intervals. That's going to be the solution set. All right. For the first checkbox, it's going from -infinity to -1. Union, the next one, is going from 0 to +infinity. And that's gonna be our solution set. All right, now I'm gonna write my solution set in the inequality form. And -infinity to -1 is x is less than -1, and then the union is or. And then from 0 to +infinity is every x value greater than 0. And now we got our answer. That's it. Quick recap. When you have that negative coefficient on a factor in the infinity table, you'll have the positive on the left side of the dot and the negative on the right side, all right? You know what to do. Like, subscribe, and comment for what problems you want to see solved, all right? Peace.